When you have gold ring, it's a shiny piece of metal, conductive, and you know the specific color of gold. But when you are going down with the dimensions to the micro or the nanoscale, the features of such materials totally change. What you can observe by the naked eye, even the color changes. Then the gold is not shiny metallic color, it's yellow nicely, but you can see the red color, violet, even blue, depending on the size and on the shape.
Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes. And of course, it's a podcast for people who love science or don't yet know that they do. And I'm sure that after today's episode, there will be way more people who love science. And maybe those who don't know will also get convinced, because today our guest is Professor Katarzyna Siuzdak, who is the head of the Department of Physical Aspects of Eco-Energy and head of the Laboratory of Functional Materials of IMP PAN. Thank you for coming, first of all.
Hello, Anna. Hello, everyone. It's a pleasure to be here with you and to share my experience in science as a woman in science as well.
Exactly. Two women talking about science today. I said PAN, which is clear for me because I'm Polish originally, but what is PAN actually?
It's an abbreviation from Polish Academy of Sciences. So in Poland, we have around 70 institutes like that, dedicated to different areas of research, different areas of science. For example, chemical physics, biology, molecular biology. And here in Gdańsk, we have the institute that is dedicated to machines. The name is more historical because here in Gdańsk, we have shipyards, but now it's not so active. Turbines you do not have only in ships, but also you have wind turbines. So mostly the activity of my institute is dedicated to renewable resources, how to use wind, water, how to use solar power to convert it to the energy. And in my team, we are working on nanomaterials, nanostructures that can be used in very smart, small devices for energy conversion, storage, and also for sensing.
Is the small part of the big part, as you said, because in general, if I think wind turbines, that's something big, right?
It's not only that you construct the whole device, but you first take the parts, but those parts are built from materials. Like you have, your t-shirt or blouse. You don't only take the sleeve and the body to put it together. You have to use the textile. Yeah. So in our case, we are working on those tiny, small materials that we build from chemicals, or we take bigger elements like gold or other metal targets. But we do not take the hammer to crush it, but take lasers like those tools to make those bigger things smaller.
But why make them smaller?
Because when you are going down with the dimensions, the material exhibit unique features. It's totally different from the situation when you are working with the bulk material. Let's focus on gold. When you have gold ring, it's a shiny piece of metal, conductive, and the specific color of gold. But when you are going down with the dimensions to the micro or the nanoscale, the features of such materials totally change because there is a different surface area, the contact between the material and the environment. You can expose different phases of the material. I mean, in the case of gold, it can be like that. And then, for example, some surface groups can be present on the surface. And what you can observe by the naked eye, even the color changes. Then the gold is not shiny metallic color. It is yellow nicely, but you can see the red color, violet, even blue, depending on the size and on the shape. So going to the nanoscale, even the shape matters. Not only, that is in the shape of ring or in the shape of some necklace when you are using some gold jewelry, But if you have the nanoparticles in the shape of some spheres, rods, tubes, it's totally different area between the material and the environment, and optical properties as well.
So it eventually means that you actually have to relearn all the properties because the ones that you see are not so useful.
Yes, totally different and unexpected one. Sometimes even the theory cannot, describe you the properties of the nanomaterials, because even the way how you obtain it matters. Yeah, sometimes the material, even the nanoparticle that you fabricate using some chemical process is different when you use some physical approach, because fabrication of nanomaterial, within this scope, you can distinguish two ways: bottom up and top down. The top down approach, you are starting with the bulk material. Let's say, for example, or consider some metallic target. And then you can try to simply take out the atoms or particles out of this target. So you would like simply just to crush it into smaller pieces, but you do not take the hammer, but you take the electron beam or laser beam that interact with this target and, just beam off some atoms that can then go together and form some particle. In the case of the bottom-up approach, you are starting with chemicals, with specific chemical compounds. For example, when you would like to produce gold nanoparticles, you are working with some auric acid or other precursor of gold. And during the synthesis, you add some other chemical species, some surfactants that affect the growth of the particle, that, for example, will hinder the growing up the particles. And this synthesis will stop at some time. You control it, of course, using different parameters like concentration of the chemical, temperature, the time. And in the end, you are finishing with some nanoparticles with spherical or some rod shape. Yeah, so using those both approach, you can obtain some fancy nanomaterial.
And what is the reason you choose one or the other?
Yeah, it's depending on what kind of equipment you are working with. It's not something like that in every lab you have different equipment. Yeah, sometimes people from chemistry are keen in this chemical processes because every parameter matters. Yeah, temperature, composition of the liquid, if you're working in aqueous or non-aqueous electrolyte. Even sometimes the volume of the flask matters. And on the other hand, when physicists mostly would like to produce nanomaterials, they're working with those physical methods, with lasers, electron beams, or other physical-based technique, chemical vapor deposition. So the choice of the techniques depends on the equipment that is in the lab and your experience, because in every technique you can specialize and know how to operate and what to change to reach in the end the material that you wish.
So what do you have in your lab?
We are working in both areas, I can admit. Initially, when I started working here in the institute, I worked with the lasers, so mostly on physical methods, and we produced gold nanoparticles using laser ablation. So this is the method when the laser beam interacts with the metal plate, and out of this interaction, the laser light is so strong that kick off the atoms out of the surface of this metal plate. And then they can agglomerate with the bigger particles or can be deposited on some substrate. But also we practice chemical approach. So also we are using some chemical sources, chemical compounds. It's both organic and inorganic chemistry, acid, salts, some surfactants. Then from those chemicals, we can produce different kind of nanostructures.
I listened to one of your interviews where you were saying that you come up with a new nanomaterial and then you find a company, or even earlier, that maybe wants to commercialize it. So do you actually consider how easy it is to scale up certain production or not really when you're trying to create a new nanomaterial?
What is funny about those material, or I can say very surprising for people that do not work with them, is that you do not really need the huge amount of them. Because nanomaterials exhibit very large developed surface area. Yeah, because you have nanosponges, nanoparticles. So the surface is much bigger than the bulk that is inside the particle. So really for some application like in batteries or supercapacitor solar cells, you do not need a lot of the materials. Mostly you're working with the very thin layers, very small amounts, and it's enough. And also there are a lot of techniques that are already used on the technological scale. For example, lasers, magnetron sputtering machines, when you would like to have very thin cover of the thin nanomaterial on some surface. For example, for automotive industry, it's already on the market. Sometimes only people work on some modifications. So both you can produce some new material, but also you can work to improve the material that is already on the market. So scalability is not the problem right now. Mostly there's a problem when you would like to use some new nanomaterial and you would like to avoid toxic chemicals or to make the whole process facile. Because of course we can use, a lot of different chemical compounds, but also we should take care of the environment. So sometimes to avoid some chemicals can make us a problematic situation.
Before we move on to discussing a bit more the nanomaterials and nanostructures that you specialize in, I think it's the good moment to ask the pub quiz question about them. So if you can ask and listeners remember, answer only at the end of the podcast.
It's very common that when people talk about nanomaterials, so when there's the kind of materials when at least one dimension is in the range or below 100 of nanometers, they try to compare the dimensions with the average diameter of the human hair. So my question is, why such a comparison is carried out? Why human hair? Not, I don't know, maybe a mug or some other piece of our everyday item.
And once again, answer only at the end of the podcast. So when I was reading about you, you were actually not talking about looking into nanomaterials, but nanostructures. And I started wondering, is that the same or it's different?
Yeah, it's the same. You can interchange nanomaterials, nanostructures. When we are in the area of nanotechnology, this nano term only matters. So we are in the range of nanometers, different kind of nano objects that can be used to form the material. So it can be the structure, it can be layer, nano layer. It can be nanomaterial. So it's the same, but sometimes it's simply like a nomenclature just to describe what is the kind of material.
Maybe a stupid question, but when I think of nanoscale, I wonder, do you ever lose them somewhere?
Yeah, of course. When you consider one nano tiny particle, you will not see it by the naked eye under the scanning electron microscope or transmission electron microscope. But of course, you do not produce single nanoparticles. You produce like a powder of them or the layer of those nanoparticles. Let's consider, the powder used during the makeup, yeah? You can see it, but it is composed by the single grains. You have to imagine that those grains are not in the dimensions of micrometers, only nanometers. Yeah, at least in the one dimension. The same is with the layers, those nano layers, nano coatings. You deposit it onto some substrate, glass substrate or metallic substrate, like on the eyeglasses. So you see the substrate, but you don't see by the naked eye how thin is this layer.
So it's not that you have it in the lab and suddenly it's like, where's my nanomaterial?
No. In most cases, we are working with some plates, titanium plates, for example, and on those plates, we are fabricating nanotubes or with a glass substrate on which we are depositing gold nanoparticles.
Let's move to applications then. We have the nanomaterial, we found it, we didn't lose it actually. And now what happens? I know that in science, especially interdisciplinary science, you meet someone, you start talking, oh, why don't we do a project together? And then you actually go into applications as well. But how is it for you? How do you decide, okay, I'm going to try to create this nanomaterial for this application?
You're looking for current needs of the community. So for sure, we are trying to adapt our materials in the energy conversion sector because we would like to use as much as possible of renewable resources. So in different kinds of novel solar cells, not only that can be used outdoor, but also use this light that is inside our buildings. You turn on the light. It's not only for reading, but nearby you can put this solar cell that will charge your phone, but you do not have to plug in, but use only the same light that is already in your room. Or for sensing approaches, for a novel monitoring of the environment, as well as the support for human diagnostics. Currently we do not only to go to the doctor, or we sometimes do not have such an opportunity to visit the doctor so often, but the monitoring of our body is very important. So if it will be possible to use such a sensor that can monitor the content of our not only blood, but also urea, sweat, saliva, to have more rich knowledge about state of our body. So in those both areas we are working, and currently it's like a hot topic, how we can use more and more renewable resources and how we can help or develop the medicine in the diagnostic.
I'm not going to go into the renewable energies because there have been a few discussions I had recently. So let's leave it a little bit aside, as much as I'm actually interested. But I wanted to go into the sensors and these applications as well, because that I haven't discussed. What I had a couple of months ago was a discussion about smart implants and the idea that you can actually monitor, for example, with hip fractures, how the fracture heals and things like that. But here we're talking about actually checking the state of your health outside of your body, let's say. So first of all, I want to understand, how does a sensor work? I press a button or I put my blood in and then it gives me the result, but it's not so easy from the technical side, I think.
So maybe let's start from the very basic one that a lot of people already use. I mean, pregnancy tests. You see those 2 red stripes if you are pregnant. This is the red color due to the gold nanoparticles. Sometimes when I ask even some people, that if you know that you already had some contact with nanoparticles and gold nanoparticles, they were surprised. Yeah, really, in the pregnancy test, they are gold nanoparticles? Yes, indeed, those red stripes appears because the gold nanoparticles are there. But what is the role of the nanoparticles in such a test? Because if you have increased level of the hormone during your early pregnancy term, they are also present in your urea. And to those gold nanoparticles, they are attached some specific enzyme or antibodies that interact very specifically with those hormones. So only the gold nanoparticles that will interact and form such a tight junction, like enzyme and antibody junction, together with the hormone or other species that are present in our human fluids, they can flow in the specific places in these tests. And then you'll see that this red color appears. So then those nanomaterials, they act some kind of host molecule to attach biological part that is very sensitive to the other chemical compound present in your body. Because, the urea, saliva, your blood, it's not only, the solution of some kind of dye and salts. There are a lot of different chemical compounds, like a cocktail. Even if you take some drugs, if you are ill, if you have some very serious disease, the human body fluids changes in the composition. So due to application or usage of different sensor, you can just track not only the presence of those compounds, but also to track the level of particular chemical compound. But in the case of the pregnancy test, you see, okay, I have one or two red marks. So yes or no. It's like a 0-1 information. But I'm working on the electrochemical sensors, where in the case of such sensors, you track the electrical signal. Because when the active molecule or the molecule you would like to detect in the human body fluid will interact with the material, just will be absorbed, and some reaction will be carried out. So this molecule can be oxidized or can be reduced. And during that process, there is a charge transfer. So the electron is going to the electrode or can go out of the electrode to this molecule, depending on the kind of process that occurs. So on the registration machine, it can be your smartphone. In the end, you see the change of the electric signal. It's like a very basic operation principle of such machine, but a lot of situation, that the whole operation principle is based on how the chemical compound that you would like to detect interact with the material.
And you mentioned gold a lot. Why gold?
Gold is very stable. It's easy to control the shape. And also because it's a noble metal and it doesn't provide any allergic situation when it have the contact with the human body. Because when we consider biosensors or sensors that should attach human body or will be operated with the humans, we also should take into account the materials that will not affect negatively human body or will not provide any allergic situations. So that is why we use titanium alloys or gold containing materials.
Okay, let's move back to the electrochemical sensors. So when we talk sensor, because you mentioned also operating and being okay for the human body, so it's not only something that we have outside, like a device, right? We can also talk about something you attach.
Yes. So you can consider two cases. Glucose sensor that you perform punctuation of your finger, you take the part of your blood, the small drop, and you put on this active area. So this active area is the sensor, but outside the body. And then you put the sensor to the machine and you see what is the result, what is the level of sugar. But also there is other solution. Now on the market, we have Libra. It's the sensor that people can simply put on the arm. There is a very small cannula, and they put this cannula under the skin, but not directly to your vein. So it's like an interstitial fluid just under your skin, the surface of the skin. And the glucose level can be monitored all the time, not only when you are doing the punctuation and then you take the blood and put on the sensor, but all the time. Yeah, of course, it's not like every second. You can just determine the time. I don't know, each hour or each half an hour, there is a measurement. What is the glucose level in my human body? So there are solutions that you can put the sensor on your skin, on your teeth, inside your mouth. You can put the sensor as an eye lens and then monitor of some chemicals inside your tears, for example. Because, every part or every our human body fluids has different composition. So then those sensors should be prepared according to the composition and the place of our human body fluids. Because we are working with nanomaterials, it's not so complicated then to produce very thin layer very tiny area and put it even on the contact lenses that we put on our eyes. So this is the advantage also to work with nanomaterials and nanostructures. Then we can put them almost everywhere. But of course, we have to take care about the kind of the materials that will have the contact with our body. So that is why a lot of people or a lot of scientists are working with the gold nanostructures, because it's well-known materials, but we can play with the dimensions, play with the shape, with the fabrication method, and how we immobilize those materials onto the surface. Because it's not only a lot of work to produce nanomaterial, but also how to deposit it on some surface, and it will stick there for the long time and still it will be there.
You just put some glue, no?
Yeah, it's not like a glue. There are a lot of different sputtering methods, vapor depositions, preparation of the surface, cleaning of the surface. Like, it's not a cleaning of the window before some holidays, but also you can use some specific alcohol, some irradiation of the surface that should be very flat and very clean, that this layer will stuck well on it.
When you're creating a new device or a new nanomaterial or anything in science, really, you have to have some test substance to see, right? I'm thinking about space, for example. You have the regolith simulant that you get to test, right? What about sensors for human body? Do you just collect your own urine to see if it works, or where do you get these from?
Of course, the first measurements, some trials, if it works or not, are performed using buffer solution, like a phosphate buffer solution, Robinson solutions, like standards also in biotechnology. But then you can even buy some kind of artificial body fluids that they mimic the composition of the human body fluids. So like you are buying some salts or inorganic materials, acids, you can buy artificial saliva, artificial sweat, artificial serum. So this is the name, and the composition is like a cocktail of different compounds that reflect somehow the composition of body fluids. Of course, your material will pass those tests. So, okay, we can detect some substance, some chemical compounds, hormones, or other species in those mixture. So this is the time that we are going to the real environment. So then we have to work with the blood, with sweat, with saliva. Of course, it's very fun. And then in team, okay, we need saliva. So who has a saliva? But when we test our sensor for glucose, and the idea for the sensor, it was to work with sweat. So my PhD students running around the city, wrapped with foil. And then when they came back to the laboratory, my PhD students collect with pipettes sweat from different parts of the human body. And then we have enough sweat for our experiments. Because, the artificial saliva is okay. Yeah, it reflects somehow the real environment, but still it's not the same.
You mean artificial sweat?
Yeah, artificial sweat.
Because you said saliva. I just want to be...
But saliva as well, yeah? So also we can provide, my students, PhD students, provide some saliva also for some experiments.
Are they aware of it before they start doing PhD with you?
Yeah, but they know that if you're working with sensors or biosensors, they should, detect some chemical compounds in human body fluids. Yeah, the first trials are with, even own human body materials.
I remember I had an interview with an expert in hair pollutants, so analysis of hair and what you can find and how you can also look at the environment and what is in and whatever. And he was telling me about his colleagues who are actually doing tests on animals, and I think some primates, and the whole story of how they got the hair from the primates, because obviously they couldn't just go and cut it, right? So there's always, I love this devotion of scientists, if you want, for the better good of science.
Yeah, and I remember also it was funny how to describe it in the article. So also we described that the sweat came from PhD students.
Did you have to name them as well? So it's like, this is
I
the
think so that
source.
in some acknowledgement we were thankful for providing their own human body fluids.
As you should for sure. Okay, we're talking in the next season of the podcast, which means that I also want to look at an additional idea about science, because I do go to a lot of conferences and sometimes I understand what is discussed, sometimes I have no clue, and sometimes I'm in between. And one of my problems is that I sometimes see, especially from the technological side, discussion of the same type of method, but with different results or with different change of one parameter and whatever. And my problem is to understand, okay, who is better or what is more important, or is this person onto something or not? So I was wondering whether I could also turn this podcast into the discussion of, okay, you, Katarzyna Siuzdak, you go to a conference, and what are you looking at? What is your interest in the field where you're in? What is discussed or not discussed? Otherwise, what is it about? Maybe we should buy something new for our laboratory because this is an interesting method.
Sometimes in the area of nanotechnology, it's not about that you will mix substance A with B and you will turn with C, and you can read it from some publication. But during the conference, some of researchers just share their tricks. I mean, some modification of the surface before, some kind of the particular compound, or some sequence of the whole procedure. I sometimes compare it with the recipe for the good cake. Yeah, of course, you can have the composition of this cake. I mean, eggs, flour, butter, and baking powder, and so on. Yeah. But if you have only the composition, it doesn't mean that you will obtain the same good cake as the person that prepared the recipe. So also the important is the detailed description, how the cake should be prepared, what should be done first, what should be done next, and how much time and so on should this process take. So the same is with nanotechnology. You can start with the same eggs and butter, but it turned out that this butter should be bought from this company because the purity in the case of chemicals is like a 99.7 or 99.8. But in the area of nanomaterials, the impurities even matters. So what is the composition of the 0.3 or 0.2% of the rest of the composition of the pure substance that you bought? So then sometimes you turn, oh yeah, my experiment fails, not because the whole path was bad, but because I bought this chemical not from this company, like the egg or the butter not from this shop, something like that. And even sometimes, the tiny stage really matters. So during the conferences, you can share and exchange your experience, the knowledge. You can ask those authors about some, I cannot say tricks, but, some specific actions during the fabrication. And also the way how they characterize the materials. Yeah. When you have this cake, you just take into a mouth and say, oh, okay, what's delicious cake? And that's all. But in the case of characterization of nanomaterials, even the sequence, what kind of method you will use for characterization of the nanomaterial will matter, because some methods even can destroy the material during the characterization. It's not like that you make the photo of the material, like the photo of the person. So during the making photo of someone, you don't destroy someone. Yeah. In some, cultures, there's a belief that when you make the photo, you steal the soul. But in the case of nanomaterials, when you perform or you use specific technique, you can even destroy the material. So in the end, the result is not the result of your material that you fabricated, but the result of some kind of destruction. So also you have to pay attention to what kind of parameters are even used during the characterization of the material. And attending of the conferences enables you to exchange the knowledge, to see what kind of parameters are used even during the characterization of the material.
You made me actually think of one more thing about quantum physics.
Yes.
Because that's the whole idea of, you observe and then you change the characteristics,
yes,
right?
It's the same. Yeah, we are in this area because it's like an application quantum physics. Still, we are using this law. We do not consider, I can say, gravity because we are working with nanoparticles. So when we are working with the solution of the nanoparticles, like this gold nanoparticles, so you do not see if those nanoparticles fall down in your solvent. They are still stable dispersion. So the gravity is not considered there. There are other forces that are more important than gravity. And it's like application quantum physics and quantum chemistry.
We're slowly drawing to a close. So I wanted to finish, before we solve the pub quiz question, I wanted to finish with your other leg of what you're doing. So, of course, the science communication part. And as we went so deep in right now, I mean, not very deep, but still, you're at a scientific conference, right? And now you're going to the public. So where is the meeting point? Where do you say, okay, this is what I want to explain to people, or this is too much, or this is something that interests me and I'm going to go for it? Because what is interesting about your Instagram profile, it's in Polish. So if you're interested, you first should learn Polish, or maybe you are actually Polish, so you can go for it, is that you don't only talk about what you specialize in. It's broad science, I would say. So where's the meeting point?
So in general, nanotechnology is a very interdisciplinary area. I cannot say that there is only physics or chemistry or biotechnology. There is something from every science space, because even considering sensors, you should take the knowledge or experience materials chemistry, organic chemistry, physics, surface physics, electronics, because you have to fabricate the prototype. Sometimes a lot of biology, medicine, because you have to explore the composition of human body fluids depending on some diseases because it change. So for me, it's a very interdisciplinary approach. And the same is about the science communication. And the idea for me was to show people that we have scientific events in our everyday life. It's not that it happens and it is it, just that we have some kind of the reason and the consequence, and we can describe how it's going on, why you are doing like that. Because we can find in the internet a lot of advices, how to cook this way, why to do this way. But sometimes those life hacks are not explained. Only, okay, do like that because it works in my home. Yeah. Without explanation, people do not understand what is the science, what is the chemistry, physics behind such an event. And I would like to show that the science is not only in the book. The science is in our kitchen, in our bathroom, and it will help us to understand our everyday life.
But some people may argue that you need more time for explanation than 1.5 minutes.
Of course, it's not like that within 1 minute or even more, this is the time how my reels last. I do not explain everything, but I would like to just ignite the curiosity, or just show, look, what's the pattern? What's the idea? What's the event? Or, it can be explained. Do not only take some life hack like a life hack and that's all. Yeah. See how much physics and chemistry is there, not only in your book that was in secondary school. So that is why I would like to make a little bit fun this science and to show it that even you do not like the science or physics and chemistry in your secondary school, it's in your life.
When I talk to science communicators, I always have to ask this question. Do you think that the school lessons could be turned into something like that as well? Or it's just two different worlds and they shouldn't mix?
Yeah, of course they could. But, also we have something like a program that should be fulfilled. Yeah. I don't know how it's with laboratories. and the access to some laboratories during school and safety issues. And of course, the feature of a lot of communicators and famous one, it's this, enthusiasm. Yeah. So also, I don't know if I should demand it from the person in the school that every day for 8 hours or 6 hours, they will be so enthusiastic and so on during the time I have, I don't know, minute or minute and a half. So I try to put my whole energy in that time. So I think that doing it for 6-8 hours, it will be not good for a teacher.
That's a very good point. I sometimes teach as well, and I'm so tired because exactly it's this enthusiasm that I put in is an extremely energy requiring thing. So yeah. Good point. Talking of enthusiasm, let's get enthusiastic about the pub quiz question right now. So if you can remind our listeners what the question was and then give us the answer.
The question was that a lot of times when people try to describe the dimensions of nanomaterials, nanostructures, they compare it to the diameter of the human hair. So why human hair, not mug, plate, or other item of our everyday life? So now the answer. The mean diameter of human hair is several micrometers, and the dimensions of the nanomaterials is we are in the range of 100 or less nanometers. So it's like a 1,000 less than diameter of the human hair, and the human hair is the object that still we can see by the naked eye. This one of the smallest object we can see by the human eye. So that is why we always compare to the human hair, that people can imagine, okay, sometimes it's even for me very hard to see my own human hair, but this object is 1,000 even smaller than my hair. So that is why you ask, okay, if we lose the nanomaterial, how we can find it? Yeah.
Yeah. Okay. Makes sense. Absolutely. That was my guess, I have to say, but I was not sure. It's always an interesting thing of science communication and finding analogies, right? There are those ones like the Schrödinger's cat, for example, everybody's talking about. But in this case, I think it is something we can still relate, and we all have the idea of how it looks, which is always very good. And what remains, of course, is to thank you so much for today. It was a fascinating ride, although short, at least that's how it felt for me, through the nanomaterials, and good luck with all your work within the Institute and outside as well.
Thank you so much.
And this is it for today. Don't forget to subscribe, to follow us on social media, suggest guests, and remember, we're also on Patreon so you can support what we're doing. This was Silax, and my name is Hanna Siemaszko.